I want to welcome everyone to the third in our virtual speaker series of Frontiers of Regenerative Rehabilitation that is sponsored by the Alliance for Regenerative Rehabilitation Research and Training. Before I introduce our speaker, I'd like to first review with you how we will do our question and answer period. Please submit your questions and then in the chat part, and at the end of the presentation, I will call your name. And once your name is called, I ask you to please make sure that your audio and your camera are turned on when asking your question. Additionally, at the end of the webinar, we'll provide the code that will have your CME credits. So please stay on at that part so you can get that code for your credits. It's my pleasure to introduce Dr. David Renkensmeyer. Dr. Renkensmeyer received his Bachelor of Science degree at MIT, and from there, he subsequently received his PhD at UC Berkeley in electrical engineering. He completed his postdoctoral work at the Rehabilitation Institute of Chicago, and he's currently a professor in the departments of mechanical and aerospace engineering, anatomy and neurobiology, biomedical engineering, and physical medicine and rehabilitation at UC Irvine. His lab invents, studies, and helps commercialize robots and wearable sensors for movement rehabilitation. Dr. Renkensmeyer holds a number of titles, including co-director of the National Institute on Disability, Independent Living, and Rehabilitation Research Program, Comet Robotic Rehabilitation and Engineering Center. He is the co-director of the NIH K1 Engineering Career Development Center in Movement and Rehabilitation Sciences, and he is the editor-in-chief of the Journal of Neuroengineering and Rehabilitation. He recently received several awards from his own institution, including the Innovator of the Year Award from the School of Engineering and the Distinguished Mid-Career Faculty Research Award from UC Irvine as well. It's really a pleasure to have you here today, and we all are looking forward to your webinar. Thank you.
Thanks, Linda. It's great to be here this morning, and I'm going to talk about robotics and regenerative rehabilitation. You can get an overview of sort of the types of devices I'm going to be talking about here. I use robotics to refer broadly to mechanically interactive systems that could be passive or active, and sensors and intelligence. So we're going to talk about some wearable sensing as well as exoskeletons and things like that. I do have some of a couple of the inventions in my lab have been commercialized, and I will be talking about those, some of the research with those. So I just want to declare that. So the first part, I'm going to just talk about why robotic regenerative rehabilitation, why pose this as something attractive to do. And then the second part, I'm going to talk about three sort of things that I think robotic regenerative rehabilitation should consider when it's optimizing movement recovery after neurologic damage. So the first part's really going to be kind of an overview of robotic therapy. This is my current lab with the Zoom picture. So I want to give credit to them, and as a very stimulating group of people to work with. So I'm going to mainly talk about people with stroke, although it applies to also, a lot of what I'm saying will apply to people with spinal cord injury or cerebral palsy. But it's about 1 in 6 will have a stroke. Stroke causes motor impairment. So here's a person tried to lift their arm. So it causes motor impairment. About 80% of people have a stroke, and it's long-term functional deficit in over half. And we've really been interested in this problem. How do you get into this state of not being able to move your arm very well, and how can you get out of it? And so about 30 years ago, I started working on robotic devices that could automate some of the repetitive aspects of motor training, so that they could be used maybe as a tool by a therapist to get a higher dose of exercise. This work was really started and pioneered by the Burke and the MIT Manus group, Neville Hogan, Hugo Krebs. And most devices used active assist therapy here you can see a device we made, New Rex, that's got 3 degrees of freedom here, and there's a gripper that you can grab, and she's reaching out for things in a kind of virtual world here to grab them and put them on a cart. And the robot's learning how much help she needs to do that, and kind of just assisting just enough. Assistance is needed. This is a typical robotic therapy result. So here we had 26 individuals with stroke, chronic stroke, and they had 24 one-hour training sessions over 2 months. We compared it to conventional tabletop therapy with a physical therapist. And here you see we do 2 baselines. This is the Fogelmeyer scale, or the change in Fogelmeyer. So I'm going to mention this. There'll be a lot of graphs like this, and I'm going to mention the Fogelmeyer quite a bit. For those of you not familiar, it's an impairment-based measurement. 0 means complete paralysis, 66 means full movement ability. And you test it by asking the patient to do essentially 33 test movements, and you score them 0, 1, or 2, and then add up the score. And the scale, it was kind of, I'm increasingly realizing, ingeniously organized to go from sort of more primitive synergistic movements, flexion synergy, extension synergy, then all the way up to moving out of synergy. So you might, for example, ask the patient to lift their arm without bending the elbow and then score that. And there's criteria, and it's repeatable if you get trained in it. And it's remarkably sensitive as well. So, so you can see, you get, the robot group had about a 3-point on average Fogelmeyer change. The conventional group didn't really have much benefit from a significant difference between the groups, high variability, and retention at 3 months. That's perhaps a little bit better for the robot. So we asked, gosh, could you do this without the expense and complexity and safety concerns of an active motorized robot? And working with Tariq Rahman from AI DuPont Hospital in Delaware, he had developed an arm support for kids with shoulder weakness, and it was rubber band driven. So we worked with him and scaled it up to a larger size, put the gripper, same type of exercise. This was done at the Rehab Institute of Chicago, the randomized controlled trial with Sarah Hausman. Robert Sanchez was the PhD student who did the engineering work here. And again, 28 patients, low Fogelmeyer scores. And we compared it this time to self-supervised training with a towel over a table like this. And you can see similar types of result. The red is the robotics technology. It's not formally a robot, but robotics technology. And then the blue is, and you can see the fall off, the retention's worse, and you get a significant difference again between the 2 groups. So it seemed like you didn't need the motors necessarily to get this kind of therapeutic effect. And here, this is the first time we asked about motivation, and people definitely, by and large, they found the arm exoskeleton to be a more motivating environment. And really, it was around 3 things. The computer gaming was fun, even though very simple games. The quantitative feedback, some people like that, and you can get a score when you're done. And number 3 was, it was this assistance provided people with a sense of causality. So now when they willed a movement, it could happen. So someone who couldn't draw a circle with their arm in space because the arm was too weak, they go into exoskeleton and they can suddenly do that. And a quote that I find very memorable is, if I can't do it once, why would I do it 100 times? And that was in response to like, why did they like the machine? Because it helps them to do it 100 times and it's motivating. So that was commercialized. This by Hokama, it was licensed from UC Irvine. They made a device that had to be very, very quick to adjust to different body morphologies and levels of weight support. So you can see kind of the knobs and adjustment here. They developed a better suite of games. And there's about over 1,000 of these in use worldwide, and there's published studies in a variety of conditions here. All right, so here's now sort of putting it all, here's a lot of robotic studies here. So there's a lot going on this slide, but let's go through it. So up at the top here first, this pink color here, the bright pink and then the dark blue, this is the distribution of consecutively enrolled stroke subjects. And this is we garnered, Mara Senesh did this work, the PhD student. We garnered data from several sources to get this. But this is related to the proportional recovery debate. So we kind of scanned some of the data that had been published on that from John Krakauer and Gert Kwakkel and others. And so you can see this kind of bimodal distribution of the Fogelmeyer. So there's people that recover pretty well, and then there's these low group here, and then this kind of intermediate group, which we have color coded. And then the lighter colors in the back is the starting distribution. So it's a little flatter. We have this low group and a high group and a little bit flatter, but they kind of, that's kind of, I like that because it kind of shows you the distribution of motor impairment after stroke. This one, we took all of our robotic therapy studies, and Steve Kramer had done this as well in the paper. These are, in each point is a patient. So this is the change in Fogelmeyer score from robotic therapy. And you can see there's this kind of U shape. So between 22 and 40, if that's your chronic upper extreme Fogelmeyer score, you're going to benefit a little bit more. And this line right here is the minimally clinically important difference. Okay, and that's taken by asking subjects, you know, is this change meaningful to you, essentially? And so you can see that you're getting now a group of people in this intermediate range where it's meaningful. This is data now where each point, number 3 here, is each point is from a study. So it would be probably 20, 30 patients for each point. And actually we have both the robot and the control groups in here, which are usually dosage matched control groups. But this is from a systematic review, and you get the same kind of phenomenon here. Okay, now interestingly, let's look at this. This is the box and block score, number 4E over here. And you can see I've got box and blocks. So this is how many blocks you can pick up in a minute versus your Fogelmeyer. And so that ability to have some hand function really emerges around 30 to 40, right in this pink group. And you see this is lifting. This is an item in the Fogelmeyer where you have to flex your shoulder but keep your elbow extended. So that'd be working out of synergy, out of the flexion synergy, because the flexion synergy means when you lift your arm against gravity, you tend to want to flex your elbow. And you can see that's right where it emerges as well. So this we take to mean that the best responders to robotic therapy appear to have a very weak cortical spinal tract, because we think the cortical spinal tract is required for moving out of synergy and opening your hand, which is what you need for the box and blocks here. So they have a present one, but a very weak one. Okay, so I'm going to try something a little different here. So I'm going to do a brain dump on you guys. So these are questions I get after my talks, and I just kind of put them, I kind of put answers here, and I just wanted to kind of, but so I'm going to talk about this, not a lot of pictures here, but I'm just going to give you these concepts after. So basically, robotically assisting upper extremity movement in a gaming environment produces modest impairment reduction. I showed you it's better for a certain group of people with weak CST, I presume. It's comparable to what you get with one-on-one therapy when you repetition match it. When you time match it, I showed you some data where it's actually better than that one-on-one therapy, but because I think that one-on-one therapy tends not to be that intense. The treatment effect's highly variable. So I estimate about 20% of participants experience a clinically significant reduction, but you have just a high variability that we need to understand better. And I showed you a little bit of the explanation, which is your starting Fogelmeyer. And then I said this, that they appear to have a weak cortical spinal tract. So what about the clinical pragmatics of it? When I go around, and we're studying this right now with Veronica Swanson, who's a PhD student in my lab. Well, it doesn't seem like the type of robot changes the treatment effect very much. We've tried different robots, more degrees of freedom, different designs, hand, arm. You can get little differences, but and you definitely have different usability and motivational and probably safety kind of things. But overall, there's been no home run with just changing the robot or the algorithm. And interestingly, robotic therapy, it can be delivered in a group setting. So that Armio Spring, or the T-Rex study I mentioned, the therapist only had to spend about 2 or 3 minutes with the patient for an hour of therapy. But you don't really see them being used that often, even though it's likely more effective. And there's a really neat study by Woneman that was published recently showing that when comparing doing Armio Spring therapy in a group versus individually, and you actually get better therapeutic effects doing it in a group. And so overall, robotic therapy devices are lightly used in routine clinical practice. So I think the size of the clinical benefit does not override the psychological overhead for using them. They tend to be perceived as complex, time-consuming. They lack a functional focus. There's fear of breaking the device. And hands-on therapy with everyday objects, the therapist is ingenious and can walk up and begin therapy immediately with no delay, and can focus on the functions that are really important for the patient and for discharge. So there's an immediacy there. What about the active assistance part? I believe it has a strong motivational effect throughout therapy. We've quantified that several times now. It may contribute to better long-term retention, and we think that might be dopaminergic, where you have better success as you're moving and you have better long-term retention. That's been shown in some other learning studies. Higher success leads to better retention. And so that these effects might be related to success rather than the movement assistance per se. So they might be replicable with sensors and gaming methods that sort of allow you to have success without physically assisting. However, as I'll show you, I do think there's probably a somatosensory component to what the physical assistance that the robot's providing as well. Okay, so given that context, why robotic regenerative rehabilitation, R3? So the rehabilitation treatment effects are modest, both robotic and conventional. That's because fundamentally people lose neural resources. They lose cortical spinal tract, they lose network processing capability. So increasing the residual neural resources is really important. And the motor system has to learn how to use any new resources. So I think robotic technologies are powerful tools, scientific tools for quantifying R3, and then also potentially for helping deliver a massive amount of practice. So with that, I'm going to then go into three things I think that you should consider if you're designing therapy and robotic therapy for after regenerative trial. This is sort of oriented toward probably cortical spinal tract regeneration. So first I'm going to talk about restoring proprioceptive integrity. So, a lot of the focus is on the cortical spinal tract, but there's other tracts and there's other things, and sensation is one of them. So before I talk about the proprioception, though, I want to just give you a concept of how I think R3 might work. And so you have a highly parallel system in the brain, okay? And what we're talking about here is some of these tracts are going to be injured or die. And we're talking about restoring some of these tracks with bridges or building new tracks. And I call it the mixed up marionette problem. So imagine you're a marionette, you're operating a marionette and you know how to do it. And then you cut the strings and you rewire them all to different places. And now you got to manipulate the marionette. So there's a lot of learning and searching that has to go on to figure out what movements are going to cause that marionette to move like you want it to. So I fundamentally believe it's going to be a search problem when we do succeed in regeneration, and that's going to be a reinforcement learning problem. And so here's a little neural network model we've made of it. In this model, you've got a bunch of neurons that are talking to motor neuronal pools, and the person is trying to get the finger to extend. You can measure the force of extension here proprioceptively, or the movement related to that proprioceptively. And when the nervous system doesn't know which of these to use, it has to try it out by practice. It has to do what I think is a stochastic search and then measure, hey, did that work better? And notice that you have a very severe credit assignment problem here. So when you get a little bit better finger extension, which of these neurons caused that to happen? It's very difficult to solve that, but there are methods to solve it. One is just plain stochastic search. And so we've modeled it, stroke recovery like this, or you could model, I believe, regenerative rehabilitation like this. And it predicts that this idea of residual capacity, where you seem to reach a plateau, but then you can always get a little bit more. And it predicts another major thing, which is you see a shift of motor activity to secondary motor areas. And we're looking at targeted plasticity with this paradigm. Notice that you need a proprioceptive signal going back here. Here's just showing, this is kind of emblematic of what happens when you do a brain imaging after stroke. So normally if I'm moving my hand, I have very focal activity, but after a stroke, it spreads out all over the brain. and you get force-related activity in more areas of the brain. And so I think that's a representative of a search that's happened to try to find other pathways. And we can actually model that with Sumner Norman, who's was a PhD student in my lab. Okay, so what about this proprioception? So this signal going back here, you need it. So working with Eric Wolbrecht, we designed this robot for measuring finger sort of flexion and extension. And we designed, amazingly, there was no good finger proprioception test. Like clinicians just say, close your eyes and they move your finger up and down. We didn't like that and say, which way did it go? So what we do is with this finger robot, we slowly move the fingers past each other. And we ask the patient, they can't see their fingers. They have to push a button when the fingers are overlapping, when they believe they're overlapping. So it's a predictive task. The fingers are moving slowly. You're anticipating when you're going to need to push that button. It's not a reaction time task. And so we use that at baseline in a study where we then delivered robot-assisted Guitar Hero to chronic stroke patients. This was Steve Kramer and Vicki Chan, who runs as PT that runs all the studies in my lab. And she, so you can see, you play Guitar Hero, third most popular video game. The robot's kind of figuring out how much help to give you. And we had people with a little bit of hand function in this one. So we had two groups. We randomized them to a high robotic assistance group and a low. So this is playing notes in a song. This is the success rate. And we titrated the robotic assistance to give one group 80% success and the other group about 50 or 60%. If we turn the robot off, both groups get it down to 20%. So they both need the assistance really to be able to play this game. And here you can see they did about 8,000 movements each over the course of the 3 weeks of training. So what's the result? Baseline proprioception error indeed predicts your motor skill improvement. So our primary outcome was the box and block scale. Here's your proprioception error measured at baseline. This is the change in box and blocks after therapy. So if you have a large proprioceptive error here, you don't really benefit from the training. And if you have more normative proprioceptive error, you do benefit. Working with Steve Kramer, we then looked, can we find neuroanatomical and neuroconnectivity analogs? We looked at about 40 or 50 sensory and motor possibilities, and we did find that injury to the sensory tract, S1 and S2, that was the strongest predictor of the box and blocks change, along with cortical connectivity between M1 and S2. And interestingly, Steve Walsh pointed out that in the EXCITE trial, constraint-induced therapy, they did a post-analysis, and patients with impaired proprioception had only a 20% probability of achieving a clinical meaningful outcome. So that was one of their strongest predictors in EXCITE, which is probably the most successful rehab trial that's been done, upper extremity stroke. Just a couple other things to relate back to my sort of brain dump. We found that, this is now Fugelmeyer going back to that, we found that people with lower Fugelmeyer scores benefited more from the high assistance. That's what this is showing. And this is, we had that motivational observation, so we said, let's just really nail it and measure it every therapy session. And indeed, the people who get more assistance report being more motivated on the intrinsic motivation inventory. And here you see again in the Fugelmeyer, you see better long-term retention with the high assistance compared to the low assistance. Okay, so that's the first. The second is synergies. And so the idea of a synergy, and this was really started by Brunstrom, and then Fugelmeyer found a way to quantify it, and then Jules DeWall, a colleague at Northwestern, has really done a nice job quantifying these. And I can't really do justice to all of his excellent work today, but the idea is basically you have these older tracts, brainstem tracts, so reticulospinal tract in green here, and I can activate it. So if I have a lesion over here and it lesions my cortical spinal tract, which is a crossing tract, if I activate the other side of my brain, I can activate my reticulospinal tract and get some movement from my limb. And this seems to be responsible for this pattern of movement, this flexion synergy pattern of movement. These tracks are malleable as well. Jules has shown with some imaging. And so we asked the question, let's try to examine this. And is there competition between these two tracks? I've already said, it looks like what you need here is a little bit of hand function, and the reticulospinal tract's not very good at finger extension. So you're probably using your cortical spinal here. So this is a plot from Maroff Senish again that we haven't published yet, but here we took data from a bunch of studies from our lab and Steve Kramer's lab and collaboratively. So each line here is a patient. So what we did is we plotted the Fogelmeyer score, but only the in synergy component on it. So normalized from 0 to 1, and then out of synergy component of it normalized from 0 to 1. And you'll hear therapists talk about patients need to break out of synergy. So we thought if they're going to break out of synergy, they should progress up in synergy for a while, and then suddenly break out and progress up out of synergy. And you can see we do find these kind of shapes, kind of L shape where you go like this. And so this is all chronic patients, and it's showing the benefit they got from robotic therapy, or the control therapy, in fact. Okay, so you get this kind of. Now we broke it down into, we have built a lot of robots. So we have some arm-focused robots, we have some hand-focused robots, and then Steve Kramer just did a really wonderful multi-site randomized control trial in telerehab that was arm and hand-focused, and got very nice results on it. Now, interestingly, look at the black lines here. These are people who they get better at moving out of synergy and worse at in synergy. Okay, so yeah, so if they're getting better at out of synergy and they're getting worse at in synergy here, and some fraction, so there appears to be some sort of competition between those two tracks, is what we think. And you can see the type of therapy produces different results in this kind of competition. So the people who are getting the telerehab and the hand tend to have that competition happening more. So we think they're having a more hand-focused thing, which is calling in their CST to play more. And then they're therefore not using their RST as much. Here you can see the point where they break out of synergy, and it looks like the telerehab, this breaking point where the line goes to slope greater than 1, happens earlier for a more distally focused therapy. Okay, so I think regenerative rehabilitation, not only does it have to consider proprioception, which it really a lot of times isn't, it's really motorically focused on regenerating cortical spinal tract, but I think it has to consider that multiple tracks, and the brain has to make a decision which one it's going to be using, and it might not be that flexible, and it has to choose one or the other, and there's some sort of competition going there. And then the last thing I just want to talk about is achieving massive amounts of practice. And I think a really seminal work was this sort of summary of a bunch of rat studies that looked at reaching after a stroke model. This is by Jeffers and Corbett's lab. And here you see that they went back on a bunch of data and looked at the number of reaches per day they were giving rats in kind of rehab practice, and then the change in a skilled pellet reaching task. And you see this sort of hockey stick where 300-400 really isn't good enough. You need to get up 600-700 a day, and they did this 5 times a week for 2 weeks. That's about 7,000 total reps. So that's a lot of practice, and that's much more than even in the recent like high dose study. I got up sort of to this range, but it's still you can think like you just need a lot of practice. I don't think it's going to happen one-on-one with therapists. Excite kind of did that 4 or 5 hours a day, something like that, but it's just difficult to do that. So we've been working on doing it. So yeah, I just don't think it can be limited to one-on-one practice with therapists or expensive devices in hospitals. It has to be truly accessible wherever you are. And so that's kind of been a theme of the lab. So we've done it with mice and rats. This is our mouse robot by Kyle Seward and Jacob Martin, working with Sunil Gandhi with AR3T support. And we have a water reward, and we can change the reward probability, and the mouse has to reach in and pull on this robot. The whole goal here was to get it so we could put it in the cage, almost like a running wheel. And so we're already up, and we haven't fully optimized this yet, but we can already get around 1,300 daily repetitions of this task. We've also done it for monkeys, working with Mark Tuzinski and Jackie Bresnahan in the UC Davis Pragmatics Center. And these animals are receiving a unilateral cervical injury, And we have a device where they can grip and pull and reach and get treats, and we can change the frequency of the rewards that are given to them, and then we quantify it all. So again, we can deliver high amounts of therapy with this, and we can measure the force of production before and after, and it's all delivered right there at the cage. Okay, so now switching to humans. So I had a student, Nissan Friedman. We developed this device for a scientific hypothesis, which I'm not going to describe too much, but it turned out people really liked it. So you see the Guitar Hero game, but now we just have sensors, which is conductive fabric. And one of my favorite graphs in my career is this one, where we gave it to 18 people with stroke to take home. The red line is what we asked them to do. This is the total number of grips, and this is days in the study. And that they had at home, and then the black line is what they actually ended up doing. So they actually accelerated it because it was so enjoyable, I guess, to do it. Now there's variability up here, so some stop, but overall, it was a good show. And indeed, when we do that, here's the motor activity log, amount of use score. The red is paper exercises in a control group. The blue is when you get the music love. And then at this point, at the 1 month follow-up, we switch over and we give the red group gets a music love. So you can see we get good nice results with that scale. Now the problem with that is only about 1 in 8 stroke patients could use that because most people who are looking for a rehab device are looking for are more impaired. So Nissan and Danny Zondervan, working with an OT, developed this puck sensor. Sorry, that's a little glitchy. Very good. And you can see a guy doing exercises in the back. You can do about 40 exercises. It senses as you're doing them, gives you music and a target. This is called Fit Me. And so the idea is that you could just get this, buy it out of pocket for a couple $100 and keep using it at home. So now we're starting to be able to do big data with it. So we have a data set. There's some probably, I guess, 5, 6, 7,000 users of the system now, but there's a data set with 2466 users. The mean number of reps they did was 13,000. You can see this sort of distribution where there's a lot of people stopped using it pretty quickly, but then there's some that are hyper users that even did 800,000 reps over the duration that they've owned the device. Okay, so we really are excited about this and ability to deliver this kind of dosage, and we want to understand why, why people exercise more at home. What keeps them going? So this was our attempt then to make it just worn throughout the day. It's not even like a workstation in your house. Now you just wear it throughout the day. So this is Diogo, Justin Rowe, and the ring's a magnet, and there's a magnetometer right here, and it counts as you're opening and closing your hand. So we wanted to give you hand count feedback, so like 10,000 steps. And just so you believe me that this thing works, here's your hand use intensity for a bunch of stroke patients, 29 versus their box and blocks test score. And this tests something called the threshold hypothesis, developed by Nicholas Schweighofer at USC. But essentially what he showed was you need a fairly high level of function in the clinic. So you can see here 20, 30 box and block score in the clinic before you even start using your hand at home. And so we verified that. He had done it with motor activity log, but here we do it with sensors. These two people, these outliers here were young, much younger, and they were college students. And so we think they had a much more active life, and these are probably just, there's sort of magnetic fields in the environment that cause a sort of false positive rate down here that's probably down here. So unfortunately, when we gave it to people, we did get them, if they got the device, they did wear it longer than if it was showing them feedback versus just the time of day. So the control group got the device, it just showed time of day, but we couldn't increase their counts. And we did get a small therapeutic effect, but this was a little, it was depressing, or we were sad that we weren't able to have a better effect here. So we're trying to explore. We think it has to be coupled with more of behavioral modification or plan, and the sensor alone is not going to do it. And then finally, Rehab Anywhere. This is work, a long series of projects, but we said, can we put the rehab right on the wheelchair? And we know that extending the elbow is something that therapists want patients to learn to get better at doing. They're sitting in a wheelchair when they're inpatient 6 to 8 hours a day. And so we have a device now that can click right into a wheelchair. And this is Marty Comelis, who's a visiting professor from Spain. And so we had versions of this that were sort of just mounted to the chair, but now we have a version called Boost that you can just replace the armrest on it. And it's got 2 modes, one where it just slides back and forth, and you can just practice extending your elbow without moving the chair. And the other one is so this is the stationary mode where you can exercise. And now we have a counter on it with a screen that counts how much you're doing. And the other mode is Overground Mode, where you can involve your impaired arm now in helping you move over ground. And we found through a series of studies that even very, very weak stroke patients, here's a guy who had a stroke 2 weeks after stroke, Fogelmeyer 25, and this is the first time he used the device. So you can see he can practice elbow extension. And then when we ask him to try to use that arm to help him propel, he can do that. So we think, it's like going for a walk with your arm. Now that you could get, the therapist can be your coach that works on quality and strategy. And then you can have these sorts of devices all around that help you get the reps in the way you would learn a sport or you would do music. So we did complete in a prior version, this was the one mounted to the device, but we did get very nice, in the subacute phase, very nice changes in Fogelmeyer compared to one-on-one therapy with a therapist here. All right, so that's my talk. I have a little video I like to play at the end here. This is from a class I teach. So the robots are aligning for regenerative rehabilitation, I think. I do think they're going to be really important scientific tools going forward. And I hope I gave you a little bit of insight into some of the things that might be considered in that. Thank you.
That was great. Thank you very much, David. So we're open to questions from the attendees. You can send that through chat or the question and answer. But we can, what I'll do is I'll give you I'll identify someone and then a second person as well once it shows up on my screen. But our first question comes from Steve Wolf. Steve, would you like to turn on your video and unmute yourself for that question?
It looks like you're unmuted, Steve, but if you're talking, we're having a little trouble hearing you.
Let me type something here.
Oh, we got you.
We can hear and see you now.
Oh,
Great.
As usual, fantastic presentation, Dave. And I think part of the concern that many of us who either are in the lab, see patients, or do both in stroke rehabilitation, addressing specifically the upper extremity, always struggle with these predictive elements as to how we can maximize improvement and how we not only invest our dollars and the time to do that, but also present compelling arguments to third-party payers for continuation of therapies which have been progressively contracted over the last decade or so. So with that in mind, I think we're all intrigued by this idea of prediction, and the nature of the question I posed was triggered by the very nice model you had of baseline Fogelmeyer scores changes by degree of severity and where they fit along the 66-point continuum. And the question that I posed for myself and perhaps for all of us is, if you're trying to presume that there are elements in the Fogelmeyer scale that indicate out of synergy movement. How many of those do we really need to predict the degree to which a person will improve with a robotic or any other kind of intervention? In the Excite
Yeah.
trial, our sweet spot based upon 3 movements, initial movements out of synergy, was exactly at 33, smack dab in the middle of the 66-point scale, which is kind of where you are here. And so the question for us is, if we're trying to justify further treatment with our patients, what do we need to be able to show a third-party payer for this Fugelmeyer assessment in greater granulation to present the compelling argument for further therapy?
Yeah, yeah, I think you're right. I think it's what I'm finding with this plot I put back up, it's very consistent with the constraint-induced therapy trial and data. And interestingly, I mean, you're talking about people now with that type of decision that are early after stroke. So if you look up here, you have this group of people that have low Fugelmeyer scores, this light peachy color here, that's early after stroke. And then, but they spread out. So some of them go here and some become these pink people. So it's difficult to know, once they're up here and it's chronic phase, you know it. But back down here, you do TMS, but I don't think that's foolproof. Or motor evoked potentials, for example, it's pretty good, but I think you could have some people who don't have motor evoked potential that end up here. These are actually the non-fitters. So if you know the blows work, then these people would be MEP negative, but some of them spread out into this pink area here. And
the reality is we get these folks at different points in their relative chronicity. And the Fugelmeyer score they have at that moment in time is their score. And that's what we're working with. We don't have the luxury often of getting a lot done in a very acute phase, that is like the first 7 days or so.
Yeah, and I think also when you think about that way, I mean, these people are getting 5 points, these are getting 2 to 3, but there's, here are some people up here that got 5 points or 6 or 7 or 8 points. There's even one here in the lower that got 5. And then you could see it in the averages, some right there, right here and here. So, I mean, would you really make a decision not to give upper extremity training to people because they weren't in this group? Probably not. So, anyway, so the point is, I think, it matches remarkably, and I thank you for alerting me to the proprioceptive aspect of constraint-induced therapy also, which I reread that paper again. It's very striking and you used a very crude measure of proprioception. You had the Fugelmeyer, which is frankly not very good, and it was strong predictor, and so I think you're going to want to look at baseline evidence that they have some cortical spinal tract available, and then you're going to look at that they have some proprioceptive integrity, which is probably important on the learning side of things, not the function side of things.
Thank you, Dave.
Thank you.
So David, I have a general question, and mine will be followed by the next in line, which will be Justin Huber. So Justin, you'll come right after me. Just a naive question. You made a comment about a third of the way through about greater benefits seen in group therapeutics versus one-on-one. And I'm wondering how you deal with that information, how you capture that in your experimental design, modifying it to enhance recovery. That sounds to me to be very important, and it's showing up through your data. So what do we do about it?
That was data from Tomoko Kitago, who's at Cornell and at Burke. And she ran a study recently where she had people paired up and do arm spring in pairs, or they did it individually. And she found that the group that did it in pairs ended up having larger changes in their improvements in their Fugelmeyer score. And when she asked motivationally, people by and large liked the camaraderie and the interaction. They didn't feel like they were being gypped, like they couldn't get enough therapy or therapist time, or they liked the context of partnership, I guess. And so, I mean, one of the things as an engineer going into this, I didn't expect psychology like to play such a role. And then when you say, oh, it's just psychology, well, psychology is neuroscience, and it relates to things like neuromodulation. So you're wondering if you're just getting a better sort of like, I'll use a regeneration term, tissue microenvironment. By the camaraderie, the tissue microenvironment improves, you know? So, yeah, so, yeah, so, you know, that, I think that needs to be followed up. You know, that's a very interesting thing. And, but again, you have a nice thing with robotics to be able to quantify that in a sort of more rigorous way, you know?
Absolutely.
Mm-hmm.
Justin, you're up next. Could you put on your video and unmute yourself?
Absolutely. This is Justin Huber. I'm at University of Kentucky. Great talk. And sorry, I got my camera on one screen, so I guess I'm looking away from you. I apologize for that.
That's okay.
I'm really excited by robotics. You know, I work a lot with stroke rehab on a Pulmonar inpatient rehabilitation facility. And just getting the reps is always like the challenge that is like a never ending and hard to achieve. But when I see robotics, I definitely see a lot of hope. I guess my question though is, a lot of these robots that I encounter are usually developed kind of with one activity in mind, and it's really getting repetitions with that one activity. And then I wonder, like, how well is that going to transfer when somebody gets out into, you know, say their home, and then they're putting on a t-shirt or brushing their teeth. But then I say, well, maybe it's just a matter of time before robots will get to the point that instead of maybe just doing a linear range of motion repeated, maybe eventually somebody can wear an assistive robot and they can use it every day and then get that task-oriented reps, which I guess in my mind, I would hope for more for neuroplasticity. And then I guess my question then would be, how do you feel like we're progressing towards that, or do you think that's something that we need to progress towards?
Yeah. Yeah, I think, you know, diversity of training is going to be a good thing. And I always talk, I think about, you know, my kids when they did music and sports, and they might have a lesson and that has a certain character to it. And then, but then they just go play the sport and do a lot of reps on it, you know, without so much. So the lessons focus more on the quality of the movement and the kinematics and things like that. And then they can just go do it, you know? And so I think so that's part of it. I think you need both of those types of things. You need quality feedback, but then you just need a lot of practice. Another idea is that there is, you know, there's task specificity for sure, but there's also just driving the system. And there might be just sort of reawakening a weak cortical spinal tract just by driving it. And I think that might come into play, and that like the drive part of it probably doesn't matter as long as you're sort of like giving attention to it, you know? Yeah. So yeah, I wish I could be more articulate about it, but I think, let me say this. I think the just pure task oriented exercise, the idea that you have to only practice every task that, you know, if you want to learn that task, the only thing you do to learn that task is practice that task. Yeah. That's a red herring. I don't think that's true. Okay. There is transfer, there is generalization, and you don't have to do the exact task to get better at it. Now, on the other hand, there is limitation to it, you know, so you do probably ultimately need to combine, you know, if you really want to perfect that, you need to bring that into the play. As far as the technologies, I mean, the robots, you can get more exoskeletal type things, but the hand really becomes a problem. Yeah. You know, so it becomes just really clunky to have a device that allows full arm and hand practice. So I think you're going to see more things like workstations. Pete Lum did a workstation for constraint-induced therapy, with just like objects on it that you manipulate. The company that I'm working with, Flint, has a briefcase now that has like 10 or 15 tasks in it that there's this SBIR grant on it. So there you're not going to get the physical assistance from the robot, but if you design the task well and the software well, you can still allow people to have success at it. I don't know, hopefully that helps.
Yeah, that's helpful. I'm very interested to kind of see how we continue to develop devices for the hand. Super interested. So
Yeah.
Thank you so much for that feedback.
Yeah. Oh, and I'll just mention one other thing there with that, the Corbett study with the rats, they weren't, no one was coaching the rats how to move.
Yeah.
So, and they improved at a skilled forelimb task, and they just did a repetitive, I think it was picking out of a grid, maybe, I can't remember what the rehab task is, but seeds out of a grid maybe. But anyways, that always strikes me too. I mean, you know, they get recovery of a skilled task without being intimately coached about the right kinematics for that task. Yeah.
Interesting. Thank you.
Mm-hmm.
Thank you. So one last question for you, David. You're funded by AR3T. Could you tell us a bit about the kinds of studies that you're doing through that funding?
Yeah. So this is with Sunil Agarwal and Eileen Anderson and Brian Cummings. And really what we're trying to do is combine, we'll develop tools and then combine the tools to look at this question of how does proprioceptive or somatosensory integrity affect rehabilitation. So we wanted to get a device that for mice, and then Sunil can do 2-photon imaging. And then we have Eileen that can introduce some regeneration into the spinal cord. And so the idea is to look at, can we get regeneration in proprioceptive systems? What does the activity look like in those systems? And then how does that relate to the behavioral drive that present with a robot in the cage? So that's the goal of that. Mm-hmm.
We have one more question. Sharon Tatum. A bit of a delay in getting that started up. Sharon, make sure your video is on and you're unmuted. We're getting connected to Sharon.
Yeah, I see another.
Can you see me now?
Oh, there you go. Hi.
Oh, okay. Hi. I had a couple questions. This is great. Thank you so much for what you guys are doing. I'm just going to pull up my questions that I had. Oh, if you could just talk to the whole process of how do you get, what's the process in terms of getting your robots out to the home? I don't understand. So is it just people in the study? Is it people that are in rehab? Is it people that are chronically, you know, they've already had a stroke, it's been years later? What kind of is that process?
Well, we've tried to, so first of all, we've never put a robot in a home. So a formal robot that has motors that can move the person around. We've never tried that. So anything we put in a home has been, the device has been more mechanical, and it's springy, or it's just sensors or things like that.
Okay.
And then we've done some of it through studies, but I think the main thing where we really had success is through this startup company that I'm working with called Flint Rehab. And they saw a need for, you know, when people get discharged out of their formal therapy, the last thing they have is a book of exercise. You know, they got a little paper exercises, and then just like they're never going to see a therapist again unless they pay out of pocket. It's an awful situation, honestly. And they're looking. Many people are looking for ways to keep motivated and keep going. So those hockey puck things, they're force sensors and movement sensors, and they designed 40 exercises with occupational therapists who's had 30 years experience and was, you know, just had this great stroke group. And you can do these exercises. There's a little intro video. So people just buy this off Amazon or off the Flint website, and they just buy it out of pocket. And then they just use it, and the only supervision they get is the introductory videos from the therapist explaining how to, you know, do the exercise well, which is better if you think about it than the paper exercises that they had, because they don't even have a video with that. At least they have a video they can play to look at doing it well. And yeah, like I said, it's been successful. There's like 8,000 people, I think, or something like that, using it at home now. We've logged, I think, hundreds of millions of movements. It's all anonymized. Like, we can't see who's what, but you can count the movements. And some people find it highly motivating. A big chunk stop using it after a week or two. And then the other chunk uses it for weeks and do lots and lots of exercise with it. So, so it's a sensor. It's bought out of pocket. It's bought from a company who can produce it at scale. Like my lab could never do that. And that's it. Mm-hmm.
So how much does something like that cost?
You can just Google it right now if you do FitMe, FITMI, and I think it's $200 or $300, something like that.
FitMe, okay.
Mm-hmm.
I had another question. Do your robots go to companies? I was recently looking for a job and I saw something called Modus Nova.
Oh, I've heard of that. Yeah.
So I didn't know if this was related in any way or.
I'd have to look up what that is. I definitely have heard that name. I'm not sure. There are a number of companies that make sensors and robotic devices.
Okay.
Yeah. Mm-hmm.
And have you considered adding in mirror therapy? Do you know what mirror therapy is?
Yeah, I know. Some people have done that using virtual reality. And so instead of the actual mirror, you do it on the screen with virtual reality. We've never tried that. So that's interesting.
I'm curious to know what would happen with your outcomes if you added in mirror therapy.
Yeah, that's an interesting idea.
I bet it would make it a little bit better. That would be my thought.
Mm-hmm. Yeah, it's an interesting idea.
Yeah. Okay, well, thank you. Yeah.
You're welcome. Yeah, and there's one more comment I'll just mention. Someone, Stephanie had mentioned about the cognitive issue. And yeah, it's Stephanie, I'd love to talk to you afterwards, but yeah, that's a big issue with any type of system. It's idealized. A lot of these systems that we've made are idealized for people that don't have much cognitive deficits. So we end up like not losing a bunch of people. So that wheelchair device, some of the device we're trying to make that just like don't require much, very high cognition to be able to use them.
Well, thank you all for your questions. I think this concludes this part of our webinar. Please stay on to capture the code that will